Okay, so the idea is on this second tutorial. So each tutorial will be on some aspect, and today is to cover what we said yesterday, which is that yesterday we put one constraint using the age of the universe. We saw that we couldn't have only dust in the universe if we consider the age of the universe. But today the idea is to go a bit more and to be able at the end. So at the end what we want is to be able to put some constraints of this form, which is saying what are the best value, the best fit from observations. So the red point, this is going to be the end of the lecture. The red point says that this is the best fit, and then you have the 1 sigma and 2 sigma contour lines. And I will explain how to do that and what does it mean in statistical definitions. So that is the idea, and that comes from some observations, which are the supernova observations. So I will explain what does it mean. So you can use that for any model. You have some model, you have some parameters free. You don't know what are these parameters. You use data from observations, principally supernova, for example, and then you do this kind of analysis. So I will not be able to run it because it's not my computer, so even the file that you see here is not saved here, so I'm not going to run it, but but you have already everything here. So so the idea is the following. No, but I will need to run it actually, but I have access to internet. Yes. So, but before going to that, first I will explain a few things about supernova, and so I will explain everything here. So, what does it mean actually a supernova? What are these data, etc. So far we are doing just background here with these are just the constraints of the background. Then on tomorrow we are going to do also with Mathematica what is called a dynamical system, and then on Thursday we go to perturbations with Mathematica and Maple maybe. But for the moment we start from the background and then we go more and more in complicated situations. So first of all, what we receive from the stars when we observe a star, we receive some luminosity, and so this we have to link it somehow to the physics that we are interested on. So let's imagine, so the tutorial also I will, once we finish everything, you will get also a copy of it. So imagine that we have a source, some star, something like that, which emits some luminosity L. And so that light goes everywhere, of course, and we are somewhere here. So we receive part of this light. Of course, we receive just a section of it. We don't receive the light coming from all the star. So what we have is that the luminosity that we observe, L, is the full luminosity divided by 4 pi r squared, which is that surface here that we have. So this is what we observe. This is the absolute luminosity, and this would be the apparent luminosity, means what we observe on Earth. Okay, so this would be in a situation where you don't have expansion of the universe, but remember that we have expansion here, so things are a bit more tricky. So what we do is that from this relation I can say that r squared is equal to L divided by 4 pi L. So keeping the same structure, what I'm going to do is that I will define something which is called the luminosity distance, and this is going to be equal to the absolute luminosity divided by 4 pi times the flux that we receive. So F is the flux which is observed, And this is just actually, this flux is just the luminosity divided by the surface of our camera or anything that we receive. So we just receive some flux and we get something like that. So this thing, we just take it from here and we are going to call that the luminosity distance. Okay, and the surface S, sorry, it's not the surface of the camera, it's that surface here, is 4 pi A0 times R squared. A0 is the scale factor today because we have an expanding universe. We said last time that we can always fix A0 to 1, so that will not be a big deal. Okay, so we have these formulas here, which is just telling us about the luminosity. So from that I'm getting that this luminosity distance, the L squared, is just, if I replace everything, L divided by L, A0 R squared. Okay, so I need to know the luminosity, the absolute luminosity of the star, which is that the star will emit. That is the luminosity that I will observe from the Earth, and that is the distance to the object. And with that I define something, some quantity, which is called the luminosity distance. Okay, so now let us link a bit all these things to get the final result. We have introduced already redshift and all these things yesterday, so it will be easier actually. So what we have is that during a time delta t, we have emission of light. So during a time delta t, the energy, we have an energy which is delta E. And what is delta E? Or what is the absolute luminosity, sorry, it's the delta, the variation of the energy divided by the, during that time E. That is the luminosity. So that is during the emission. So during emission, there is some energy which is emitted during some time, t, or delta t, and that is the luminosity. This is how it is defined. The variation of energy divided by the variation of time. At the same time, the apparent luminosity is exactly the same, except that the apparent luminosity is just the delta E at the reception, means on Earth, divided by the time of observation. Okay, so these are the definitions of luminosity. This has nothing to do with cosmology, it's just the general definition of what is luminosity. So for the luminosity distance, we know that we need to calculate L divided by L. So we get that this is the delta E at the emission divided by delta E at the reception times the delta T at the reception divided by the delta T at the time of the emission. Okay. So we have to calculate actually this, and this is the main thing, how to calculate this. One is simple. One is simple, is just the variation. We know that the energy which comes from a photon is like that, hc divided by lambda. So then we know that the delta emission divided by the delta E at the reception will be what? Will be just the variation of the lambda will be just that according to this formula. And this is what we defined yesterday. This is just the redshift. So this is the wavelength that is that we measure on Earth compared to the wavelength which is emitted by the source. So the source emits some wavelength, but because of the expansion of the universe, this wavelength changes. So its energy changes, and this is related to what we define to be the redshift. So the last one is just the definition that we used yesterday to define redshift. At the same time, the speed of light being a constant, if I define things in this way, we know that the speed of light, I can say this is the lambda of emission during the time of emission. And this is also equal to lambda at the time of reception in this way. So then I have that delta T reception divided by delta T emission is equal to lambda reception divided by lambda emission. And this is 1 over 1 plus z, sorry. So from that we conclude that L divided by L is equal to 1 plus z squared. So replacing in the definition of luminosity distance, we get that the luminosity distance is equal to A0 R 1 plus z. So this is just a small algebra actually, which is relating what we call the luminosity distance. We will see how to link that to observations, and the redshift and the distance R. Questions so far? Yes.
So in that, L is equal to L upon 4 pi r square. So the radius is that the distance from the center. So that should be the function of t because that's expanding. So why we don't take account?
No. There are two distances. One is the co-moving distance, which is not changing. If I multiply it by a scale factor a, that is the real distance. The real distance doesn't change, but I can define a distance which is not changing. In some sense it goes with that, but this I keep it fixed. If you want, in the metric, I have something like that. This R is what we will call the co-moving actually radius. That doesn't change. That doesn't change with time, okay? But AT times R is the real distance. So the real distance between an object and me is AT times R. And that changes with time. But R doesn't change with time. Okay, so we have that this factor is equal to 1 plus z. This luminosity distance is proportional to that. And I can always, as we said yesterday, fix this to 1. So I can kill it, it's not important, it's just a factor of normalization. I say that the scale of the universe is 1 today. This we can always do it. And so to conclude completely, I need just to calculate R. And R is something that we calculated more or less yesterday. So let me do it again. This is from here. We know that for light rays, dS squared is 0. I'm considering that we have a radial light ray, so there is no change in theta and phi. So then I get that dr is equal to dt divided by at. And we take the integral of that, and I put from 0 to t. And so that is going to be my distance that I will need for the luminosity distance. Now this I can change as we did yesterday, so I'm not doing it again. You just change this into redshift, and it goes from redshift z to 0 So I can write it as the integral from 0 to some redshift. I should put a prime maybe. Okay, so this is the R. And so yes. What is the question of R? Yeah, this is the Hubble function H, and this is it's a function of Z prime. I don't do again this calculation, but you just remember the relation that the A of t, we did it yesterday, is this. So if I take dA dt, it's equal to minus 1 plus z squared dz dt. So then I have a relation between dz and dA, so I can replace here and do these calculations. Okay, so then I finish actually this part, and I have that the luminosity distance is equal to R, this is R, times 1 plus z. Let me put back the constants because they are very important now. There is a speed of light that I considered equal to 1 all the time, but now we will need it because we will compare directly to observations. There is a factor 1 plus z in this. Okay, so this is our last formula of what is the luminosity distance.
What is dash here?
Huh?
Dash, Z dash, Z dash?
No, yeah, I just didn't, because I integrate to z, so I didn't want to use the same variable. So I should maybe write it, I don't know, x. Okay, so the thing is that it's just that, okay, this is the luminosity distance. What it tells us is the following, is that because the universe is expanding, the Hubble function is telling us about the expansion of the universe. So then you get some change in the luminosity that is emitted and the luminosity that you observe. That comes just because of the expansion of the universe. So this is what you see here. More the redshift will increase and more you will have this effect. Now the thing is that we don't observe that, but usually you link it directly to the log of this. This is the log that we observe, and the logarithmic of this is called the magnitude of an object, of a star or any other object. So in the sky, the object which has the highest luminosity is of course the sun, and then the second one is the moon, and then the other objects, they come after. So what we define is something which is called the magnitude, and it's just 5, the log in basis 10 of the luminosity distance divided by 10 parsecs. So this is just actually some sort of definition of what is a magnitude. This is called the apparent magnitude, and this is the absolute magnitude. Okay. So this is all what I wanted to say about that. So now we have two things. One is that we can get it from the observations. Imagine that there are some stars. We know exactly what is their absolute magnitude. We know how much shiny they are. We know how much light they produce. So these are going to be some sort of standard candles. So we know what is this. This is what we are going to observe from Earth. This is the apparent magnitude. So for each of them, we measure what is m. And we measure also at which redshift that star is. So we have this, and we have the redshift. So then, from this formula, I can say what is the luminosity distance as a function of redshift. For different stars, I can say exactly what it is. So this will be from observations. Now from theory, I know that luminosity distance is this, so I know how it changes with redshift according to some Hubble function. So now I can compare the Hubble function to the observations, in the sense that the Hubble function depends on many parameters. So I can fit these parameters thanks to these observations. So what are these observations that we are going to use? They are called supernova of type 1a. Why type 1a? Is that there are different stars, actually. When a star will explode, there is, at the moment when they explode, when the energy is really at the peak, you ask if the star has some hydrogen or not. This is the first question you ask. And you have two possibilities. It's a yes or it's a no. If it is no, you call that a type 1. And if it is yes, you call that a type 2 star, supernova. Now, what we are interested on are this type 1. You ask if they have silicon, and you get two answers, yes or no. If the answer is yes, you call that 1a. If the answer is no, you call that 1b or 1c. And this 1b or 1c, then you ask if it has helium. Then you have two answers. If yes, you call it 1b. If no, you call it 1c. So this is the classification of that. You just look to their composition. So when I'm saying that I'm looking to supernova of type 1a, means that they don't have hydrogen and they have silicon. This is what it means. Okay? So this is the composition of the star at the moment of explosion. Of course, during their life, they have different chemical elements, etc. But at the moment of explosion, they have some very specific composition. So that depends a lot also on if it was a small star, a big star, etc. They produce different type of elements. The second thing is that the very interesting thing about this supernova of type 1a is that they are binary systems. So you have two stars, and what's happening is the following: is that you have a bigger star and you have a small star. So the bigger star will start actually taking matter from the second one. So here, usually it's at the beginning what is called a white dwarf. So a white dwarf is some kind of star which exists. It doesn't have much more nuclear reactions into it, but it still exists just because of the Fermi pressure that the electrons, they cannot, because they are fermions, they are the Pauli exclusion principle, they cannot all go to the fundamental state. So then they have to keep some energy. So because of that, you can see it as some sort of pressure. So because of that, that star still exists. But now you start accreting matter. So matter is, that star becomes much more massive. So you get much more pressure. Because of that pressure, at some point of time, the pressure is not enough and the star just collapses a bit and then explodes. And it reaches a limit of mass, which is 1.4 solar masses, and then it explodes. That limit is called the Chandrasekhar limit, and you cannot have more than that. That if you increase the mass more than that, the mass is not, it's too much, and the star just collapses, actually. So this is the Chandrasekhar limit. It has been done by Chandrasekhar in the 60s. I think it was in the 60s. So you have some limit on the mass. You cannot have much more than that. You cannot have this type of stars which are 100 times the solar mass. So when you reach that limit, you explode. So what is interesting between these stars is that they all explode with exactly the same mass and the same composition. So they have exactly the same luminosity, because if you take a star which has carbon or a star which has hydrogen, they don't produce the same light. But if you take two stars which have exactly the same chemical composition and they have exactly the same mass, they produce the same luminosity. So this is why they are standard candles. So how do we know that? It has to be first a binary system, and two, it has to have exactly this composition. So from that we say they are supernova of type 1a, and we know that they have all the same luminosity, absolute luminosity. They have the same magnitude. So this is why we can consider them as standard candles in the sense that they have all the same absolute magnitude, which is of the order minus 19, I think. Something like that. Or minus 9. No, 19. Okay. So this is the data that I will talk about. So this is what we have. This we call it mu. So the data are telling us that from the data they observe this. We have a camera on Earth. We measure what is the luminosity we receive. We know what is this. So we know exactly this mu. And we know at which redshift the star is. So then we have mu of z. So we have some mu of z observed. Okay. And for us, we can calculate the mu of z theoretical one, which means with this formula. So then we can compare the theory with the observations, which are going to give some constraint on the luminosity distance, means on the Hubble function. So this is what we are going to do. And so the first thing, okay, so Mathematica file, for the ones who want to know a bit about it, I will put it, maybe we will share it for the ones who want to use this kind of data. So first of all, this clear all global is just something to erase everything. So if you had some variables that x has a value 2, 3, etc., you just erase everything with that. Now we need a file of data. So I will go on a website, which is, the website is the following, of the group which is doing these observations. You go there and you download actually. It's called supernova.lbl.gov union. Okay, so this is the website. So let me see if I have internet. Then union.gov, government, G-O-V. Okay, so I will write it here. You can look at it here. Supernova. Okay, so this is the group, Supernova Cosmology Project. So they give all the data, etc., for this supernova. And what we are going to do is to use the file, which is here. It's called Union 2.1. And this is going to be the file. So how it comes with one side is the name of each star. Here, this is the redshift, at which redshift they have been observed. This is this parameter mu, mu observed here for each of them. This is the error that you have, the mistake that you have, the precision that you have on the mu. And this is just some kind of normalization of that, but this is not important. We are not going to use it. So we are going to use only these columns here. The name is not important. The redshift, the mu, and the error bar actually on this mu. Because of course you have always some precision on that. Okay, so let me download it. So one thing is that when you have some data, you have to first import this data. So import, and then you put where it is. It is in the thing which is called download. So the only thing I said is that we download something which are data in order for the system to understand what it is. And what I downloaded, I call it SN1 data. If you want to see what it is, which is just the file that we have downloaded. So for each of them is the name, the redshift, the mu, etc., etc. So we have all the data which are imported. So now we can work with it. So we can work with it. So what I'm going to do is just a loop where I say that the second column is what I will call the redshift supernova. The third column, if you remember, is the mu observed. And the fourth column is the sigma, so the error bar. So I'm just making a loop on all the values of I from 1 to the length of this, so how big it is. And you run this. Okay, so once we have this, we have these three quantities, redshift, mu, and sigma. We just put them in a table, and I will call that all. So which runs from 1 to all the thing. So so this is all the data that we will use. This is just something which says that we use error bars, and we run it, and this is the data. So this is what these people, they observe. They observe the redshift, and they observe the mu at different redshifts. So this is one supernova of type 1a. They observe that the mu is equal to 44, more or less, with this error bar at 1.2. So this is all the data we have. As you can see, of course, we have principally data at small redshift. So here, because means that there are supernova which are close to us. The supernova which are very far from us, so at high redshift, we have very little data. We observe just like 10 or 15 of the supernova. So some of them come with a very good precision, and some others, they don't. Okay, so what we want to do is to compare that to the theory. So how to compare that to the theory is just this. We have this function now. We have this function which is just 5 log of this. So, and dl is this. H, we know what it is. So then it's easy to do, is that maybe just to explain which model I consider. So this is the model I was talking about yesterday. This comes from the Hubble function. The Hubble function tells us that 3h squared is equal to 8 pi g times the density. And so from that, we could write it yesterday like h divided by h0, or h squared, is equal to some omega m0, 1 plus z cubed, and some omega lambda if I have a cosmological constant. So h is just the square root of this. Okay? So this h here, it has an h0. It's c divided by h0, 1 plus z, and the integral from 0 to z, dx divided by the square root. Okay? So you choose a parameter omega m0, then you can do this integral. You multiply it by ch0 itself, you have the luminosity distance, you take the log of that, and you have the theoretical value. So let us take, for example, I don't know, something which is, so I took h0 equal to 70 km per second per megaparsec. This is the speed of light. This is the h I said, the square root. So this is the theoretical mu. You run it, and then I will take, so first of all, I will take just matter in the universe. So I will not run everything, because even just for a plot it takes some time. So this is a universe with only matter. So there is only dust in the universe. As you can see, we don't fit very well. I mean, the data are a bit, we should be a bit higher like this. So we go like this. So this is the theoretical value. So we don't fit it very well. So what we need to do is to introduce a cosmological constant. So the value of this cosmological constant, let me put like 50% of matter and 50% of cosmological constant. So then it gets a bit better. If I go to 30%, then I'm getting a much better fit, etc. So the question is that what is the theoretical value which fits the best the observable? But we see that if we don't have a cosmological constant or we don't have dark energy, definitively we don't fit well this data. So these are the data which in 98 we didn't have all this. There was only 45 or 47 supernova. Now there are like 500, so we have much more data. But in 98, when they did that, they had some few data, and they could see that we cannot fit it with only matter and radiation. Radiation is completely not important here, but we can add it and it will not affect at all. So we could see that clearly we need to add a constant, a cosmological constant, or dark energy, or whatever we call it, in order to fit the data. Otherwise, it doesn't work. Otherwise, the magnitude, the luminosity is too large compared to the observables, to the theory, sorry. So this is just to see that, but now we have to do statistics to see exactly what is the best fit. So how we do the statistics, the only best thing to do is what is called a chi-squared. Chi-squared is very simple. It's to say, I will make a summation on all the supernova I have of the theoretical mu at some redshift z minus the observable mu squared divided by the error bars that we have. Okay? So if the theoretical value is very, very close to the observable value, I mean, if it is exactly the observable value, then you just make a summation of 0 plus 0 plus 0, and chi-square will be 0. But if you have something which is which fits very well, this function, the chi-squared, should be a minimum. So when it takes the smallest value, means that you have the best fit. So you just change your parameter. We have here only one parameter. This is omega m0, and because this is 1 minus omega m0. So you have only one parameter. You take every time a different value of this parameter, and you run that. And for each of them, you get a chi-squared. So then you get a chi-squared as a function of omega m0, and you will get something like that. And the minimum will be around 0.3. So then you would say, okay, this is when I fit the best, actually, the parameter, because clearly this is the minimum, so the theoretical value is very, very close to observational value. So what we have to do is just to do this calculation, which is this. So this is the theoretical value minus the observational value. You take the square of all this and divide by the error bars that we have. So this, I'm not sure the computer will be able to do it. So then I'm looking to minimum. So you just ask, find the minimum of this thing with the parameter omega m0, which runs from 0.1 to 0.5. This is something I did before, so we don't even have to run it. So you get that the chi-square, the minimum is this, that doesn't matter, and the best value is 0.28. So 0.28 means that you have 28% of matter in the universe, and the rest of it, 72%, is dark energy. So this is what you will see in most of the, even on whatever website or book, etc., that you have more or less 70% of dark energy, 30% of matter, etc. Yeah, it will have difficulties, I guess, with this computer. So, so this comes just from the supernova. Okay. Do you have questions so far?
How many data are there in Millia?
Actually, it's more or less the value of the minimum. So it's 520 or 530 data, something like that. So then you can run that for any type of model. And so let's continue on that. So then you can just use any kind of theory you want, and you have some parameters. And you use this data, but you can add some additional data, not only supernova, and you run that, and you get the best fits. Okay. So now we continue on that. You have the best fit. That's not enough. So I'm calling again this file, etc. So that is okay. But now what I did is to consider a dark energy model. So a dark energy model is the following. Because imagine that you don't believe in the cosmological constant. You say, no, I mean, cosmological constant, maybe it's not correct, etc. Let us look to something else. So remember that I was saying that, okay, this is the Friedman equation. And you can add all type of matter you have. So you have the density of matter. You can add density of radiation. You can add density of neutrinos. You can add density of some dark energy, etc. All type of densities of fluid that you want to consider, etc. So let us take radiation and neutrinos. They don't affect anything at this very low redshift. We had very small redshift. They have no effect at all. They have effects in the very, very, very early universe. So what's happening is that you have some dark energy component. Yesterday we said that we can define some equation of state of this form with some W. And I will consider W to be constant. So I would like to see what is the constraint on W. For the cosmological constant, W is -1. And if the data is telling us that it's not -1, then it's not a cosmological constant. Okay. So then you do this same thing, the same game, and this is what you get actually. You get that the best fit is omega m0 equal to 0.28 and W equal to -1.00449. So supernova are saying more or less it's a cosmological constant. Or if it's not a cosmological constant, you have to be very, very close to it. But this is just the best fit. You have always to see what is the error bar, what is the 1 sigma, what is the 2 sigma. So 1 sigma means 68% of confidence, in the sense that imagine that you have some probability distribution, which is a Gaussian, and with some parameter x, and this is the best fit. This is when the probability is higher. What we call 1 sigma is this, is that when 68% chances, so the contour at 1 sigma says that we have 68% chances to be in that region. 2 sigma is more or less 95%. So you say that I'm sure at 68% or I'm sure at 95% that I'm in that region. So you have to know how big is that region. So the same thing actually, you calculate this 1 sigma, so you will have the file to do that. So let me go directly to it, and this is the final result. So this is the best fit, as we saw before, that you get something very close to -1, and you are here. So this is 1 sigma, so it means that all that region here is 68% chances, and the big one is 95%. So what you are saying is that, okay, this is the best fit, but the best fit doesn't mean anything in observations. What is important is that is it allowed to be here or not? Yes, there is 95% chances that maybe the universe has this value, or this value, or this value. So what it says is that actually supernova, they are not constraining so much the data, in the sense that, okay, this is the best fit, but you have 95% chances to be everywhere here. And if you are here, definitively it's some dark energy model, which is called phantom dark energy, or here, etc. This is not at all anymore the cosmological constant. We can reduce a bit the size of that by using other data. So this is just supernova. You can use CMB. You can use, CMB. you can use, it's not coming back. You can use CMB, you can use what is called BAO, and some other observations, which are going actually to reduce a bit this, this size, and it will be a bit smaller like this, something like this. But still, we have some freedom, okay? So data analysis actually is something very simple, and that I guess everyone can do, because it's really just with Mathematica. We don't need a big thing. And it's interesting because it brings some constraints on the parameters. We are not just saying that the parameters can take any value, and at the same time we are saying which is the correct model. So for the moment, the best model is the cosmological constant model, that you have dark matter with cosmological constant. Okay, I don't know if you have questions.
Could you explain again how to compute mu theory omega m set?
From, yes. Maybe I should not erase that. Okay, so the thing is the following. The mu is defined as 5 times the log in basis 10 okay, and the luminosity distance is c 1 plus z, the integral from 0 to z dx hx. Okay, so the thing is the following. Let us consider, I will do it algebraically, some universe with only matter. The Friedmann equation that we calculated yesterday says that we have then this equation. Now I divide by 3 and I get this. Now what the density of matter, we saw it yesterday, we can write it as with the redshift in this way. And if I take this relation at z equal to 0, I'm getting that h0 squared is 8 pi g c4 rho m0. So this constant is more or less h0 squared. So I'm getting that h, it's h0 1 plus z 3/2. This is also a calculation we did yesterday. So then I can do this integral. This integral here is just h, it's h0. I can just remove it. So it's c divided by h0. And there is a 1 plus z here. And I integrate from 0 to z dx h, not h, 1 plus x 3/2. So this integral, I can do it, is 1 plus x minus 1/2 minus 2 from 0 to z. So in 0 it gives 2. And minus 1 over 1 plus z squared. Okay, so we do this integral, etc. We get something like that. So this is the luminosity distance. I put it back here. I'm getting mu as a function of z. I just need to know what is the speed of light and h0. That's it. Okay, so this is why I had to fix 2 parameters in the file, which are the speed of light and the value of h0. Yeah, so in all the things I took here the speed of light in kilometers per second and h0 70 kilometers per second per megaparsec. And then from there I just did the calculations. Other questions?
How we can learn this programming, because this is just representation. We are seeing some coding, but from there we can learn now.
By questions. Tell me, have you used Mathematica before?
Yeah.
Yes?
But not very much, only the basic, solving the differential equation, plotting the graphs.
Okay.
And
practice.
Yeah.
You have to practice.
Yes.
Have you the whole inbuilt functions, or you have written your own?
No, this is just my own program. This is why I was trying to explain step by step, because just to show that it's really not complicated. So there are just very few steps. One is to call your file, import. Two is to put the file in different variables. One is redshift, one is mu, one is sigma. It's just ordering a bit things. So you just call this thing here. This is the second column, the third, and the fourth column that we have seen. And then this, you put it in a table that you say that in each value, you get z, mu, and sigma. And then that's it, actually. Then you have a function which is called error list plot, which is plotting these kind of things. And then it's just, actually, in terms of programmation, it's not very evolved, because what you have, it's mostly just summations and things like that. You have just these summations here. So this file, actually, I don't know how we distribute them.
Now you give it to us. We'll put in the lab there.
Yeah.
And also send by mail.
Send by mail. Okay. So it will be sent by mail, just to have an idea of this.
We are going to distribute only to those who are registered here.
Yeah.
On this all material.
Mm-hmm.
That's all.
Yeah, so then, I mean, I don't think, the thing is that for the people who have a computer, the idea was to do it at the same time. But finally, maybe we didn't do it in this way. So then after that, there are just summations and things like that. It's just to know how it works, statistical
I think
things.
from tomorrow, if we bring computer, 3-4 people
Yes.
together, it will be fine. It should be fine.
Yes.
Most of our people has mathematical 10.
Mm-hmm.
Anna? We have, so you bring your laptops, and even if it is between 4 or 5, it is fine.
Okay.
It will be fine.
Because I,
It will be
better.
yes.
And
Because I've seen that not so many have had a computer, so I went a bit fast on
this
it.
program will give to them, they'll learn on their
Yes. Okay.
own. Yeah, that's it.
But maybe to send the program just before for everyone to have
Yeah,
it.
before.
To have it
So if
directly
you
on
give
the.
tomorrow morning, we'll send, and then they can download.
Okay.
Or we'll keep in the USB, they can copy. That's also fine.
Okay. Yeah.
That's fine. It is fine.
We can go to a second program.
So today they'll get all notes today, because I've given to them. They can copy or they'll get by mail.
Mhm.
All will get by mail.
Okay.
And once I get, and then we'll print.
Mhm.
Before they leave, they'll get print copy also.
Okay.
By now, I have just sent soft copy to this people. They'll mail today after course.
Okay.
After this lecture, they will mail immediately.
Uh-huh.
So by 4:30, you finish. What time you finish? Within half an hour, everybody will get.
Okay. Because then we have to transfer again another file.
Not tomorrow. Tomorrow I'll bring this adapter.
Okay. So yeah.
So you can,
so
if
we
you
do
want,
it.
you can take tomorrow half an hour extra.
Okay. So then we do it tomorrow, because otherwise
If it is creating problem,
it will
let's
take
do
time
tomorrow.
again. Okay.
There's
Sure.
No issue.
Yeah. Sure.
Tomorrow we will have more half an hour extra, and
Mhm.
then you can do tomorrow.
Okay.
There's no problem.
Okay.
And better, right? No? Because all will run also, and all will have computer. 4 के बीच में एक करा तो भी ठीक है. They'll have live demo. Is it fine?
Yes.
Yeah. So that's perfect. And also, there are some maple sheet if they want to see how to generate all those first.